All right, enough hubbub below. Let's focus. So again, we're still in this program of trying to do the Shor's algorithm, number factorization, and in here, well, at some point in the lecture we'll go through the strategy again, and we're still one of the components, one of the ingredients for the factoring algorithm is going to be a phase estimation. And I introduced it briefly, and in the previous lecture we did kind of a lab session where we did some computations. I'm going to recap that and then make some more precise statements and just start setting up at the end of the lecture, start setting up the implementing the factoring algorithm with the quantum computing. So let's recap where we were. So if we have a unitary operator U with an eigenvector U and an eigenvalue given by this, we say that phi is the phase, and phi technically can be any number between 0 and 1. In the computations that we did in the previous class, we assumed that if phi actually has this base 2 decimal expansion, so given by this, then we can recover phi using a quantum circuit. And what I want to do is I want to describe this quantum circuit, and in here we have a pretty strict restriction that it has a terminating expression for this base 2 expansion of phi, but technically phi can actually be any number 0 and 1. Here's a quick warm-up problem exercise. What's the base 2 expansion of if phi is equal to 1/3? What is the base 2 expansion? So I'll give you a second to look into it. In base 2, it's going to be 0. 0. I know that for sure. I didn't do this ahead of time, so we're going to do this in a democratic way. What's the next one? What's the next digit? 1. What's the next digit? 0. What's the next one? What's the next one?
Can you explain why?
Yeah, why 0, 1?
I can guess the pattern, but...
Yeah, so let's add a page here. So we want to write 1/3 is equal to, it's going to be A 1, 2, so it's going to be 1/2 plus A2, 4 plus A3, 8 plus so on. And essentially, the way that I'm going through it, if I'm going digit by digit, and maybe we can make it more precise, is if I put 1 in A1, it's going to be great. It's going to be 1/2 or greater, and that's going to go over it, so it has to be 0. So it's going to be 0, and then 1/4 is going to be less. So that's going to be, what I have left over is 1/3 minus 1/4, and that's 4 minus 3 over 12. It's going to be 1/12, and so 8 is going to be 0, and it's, yeah, now I remember. It's a geometric series. You can prove it like a geometric series, where it's, let's see, it's going to be, so on the right-hand side, it's going to be equal to AK over 2 to the k from 0 to infinity. And the pattern that we've seen so far is that it's every other one, right? So the claim here is that this is equal to 1/4, 1 over 4k, k from 0, k from 1 to infinity. So this is if a k is equal to 1 when k is even, and 0 if k is odd. Right? So far, so good? So this is the claim, and this is a geometric series, and we can just compute this. So the answer here is going to be 1/4 divided by 1 minus 1/4 is equal to 1/4 over 3/4. So it's 1/3. So that means that 1/3, the series, the base 2 expansion is going to be 0, 1, 0, 1, 0, 1, 0, and so on. So it's going to be alternating zeros and 1, and it's not going to terminate. So the reason that I wanted to include this example is because that's a very simple phi between 0 and 1, which is a fraction in base 10 or in the typical numbers that we use, which doesn't have a terminating base 2 expansion. And so this restriction that has a terminating base 2 expansion is fairly restrictive, and it doesn't even cover the rationals. So that's part of what I wanted to say. And the reason that I knew that it wasn't terminating is because now I remember. I knew that, for some reason I knew that it didn't terminate. And I remember this from geometry. In geometry, there's this claim that you can't trisect an angle using a straight edge and just a straight edge and rule, whatever. I forget what, a compass, yeah. You can't trisect an angle. And so, but you can bisect an angle. So with this series expansion, you can actually get arbitrarily close to trisecting an angle if you just do a bunch of bisections. So back when I was a kid, I was like, we can get arbitrarily close with human error as trisecting an angle. So this is my attempt at trisecting an angle using a series expansion. So that's how I remember that you could get close to it using bisections. But anyway, that's just lore of my childhood. So anyway, this is the whole point, that we have a circuit that if phi has a terminating expansion, then we can compute the phase. but it's not going to work in general, so we'll discuss what to do when it doesn't have a terminating series. So in here, what we have is this circuit to compute the phase. So this is the first part of the circuit. You start with all zeros, you apply Hadamard gates, and then you have your eigenvector u, and then you have a bunch of controlled u gates here. And they're controlled by the jth u gate is controlled by the jth qubit. And in here, what happens is that each of these vj's, each of these outputs, you can write them this way. So the result is going to be a superposition of 0 and 1, where the phase in front of 1 is going to be equal to this. And I guess I'm forgetting, I think I do it consistently throughout the lecture notes. I'm forgetting to normalize things. But in any case, you have this phase. And what I'm actually doing is I'm going to rewrite this term as, I'm going to bring a 2 to a t, and I'm going to divide 2 to a t. And in particular, the reason that I want to do this is because I want this to be an integer. And this is going to be true based on our assumption of the terminating base 2 expansion. So I write this explicitly here. So in here, our assumption has that we have a terminating base 2 expansion of phi, which it terminates at t positions, which is the number of qubits that we're going to need to measure it. And this expansion is equivalent to this number. And in this case, if we multiply everything by 2 to the t, then it's plus t, and plus t. We see that this number is going to be an integer between 0 and 2 to the t minus 1. And I'm going to call this number phi bar. And this is going to be an important property that I need. And this is why I want it to be terminating, so that if I can multiply it by a large enough 2 to the t, then phi is going to be a number. And in here, just using the substitution, I write that phi bar is 2 to the t. I can write that psi j, the phase, is going to be given by 2 pi I phi bar over 2 to the t minus j plus 1. So this is half of the circuit, and I prepare them in this way, each of the phi psi j's, and then to finish the circuit we need this observation, or recall the definition of the Fourier transform and its circuit. Although we're going to black box the circuit, but we recall the operation of the Fourier transform. And again, the Fourier transform here, it's going to be only for a certain range of numbers. And it depends on the number of qubits you put into the circuit. And if you put t qubits, then the Fourier transform only works for the integers in this section. So that's why I want my phi bar to be an integer in this range, so that I can take the Fourier inverse. And recalling the definition of the Fourier transform, it takes an integer in this range and it maps it to this product of qubits, where you take 2 pi I times m and divide by 2, and then for each product you increase the power of 2 in the bottom until you get to the last one where the phase is 2 pi I m over 2t. So this product of qubits, you can actually write it this tensor product where it's 2 pi im divided by 2 to the t minus j plus 1. So in here, you have that the phase is increasing or decreasing depending on which way you see it, but the powers of 2's are consecutive. And I just recall now the way that I prepared my psi states, and it's given by this formula where we have here the powers of 2's, and then we have phi bar, which is in this range, which is important. And we have that this tensor product of qubits is equal to this. And the thing to note is that it matches this. So it's the same definition as the Fourier transform. And the only thing that we need to do is substitute phi bar for m. And so that means that if we take the inverse Fourier transform of this state, then we're going to obtain phi bar. Where phi bar was our 2 to a t phi. And phi had the terminating expansion. And so this way, using the circuit here, this is the diagram, the cartoon for the circuit. We can do, and here there's going to be t qubits. And then we have our eigenvector. And for each of the qubits, we have the Hadamard gate, and we have a controlled U gate, which is 2 to the j minus 1. And then once we do this for all the eigenvectors, or all the qubits, all the t qubits, we take the Fourier inverse, and the output here is going to be the phi bar. So this is going to give us the face of this unitary operator. The key part here, though, was that it had this terminating expansion, and depending on where it terminated, we included those number of qubits to actually measure p exactly. So it's going to give us the phase factor 100% accurately. The problem here is that if the base doesn't have a terminating base to expansion, then this is not going to give you the phase very completely accurately. For instance, even if we had this phase or this base expansion up to t numbers or t bits, and we included less than t bits here, then the Fourier inverse is not going to give us the phase precisely. It's going to be a mixture, a superposition of different numbers. And somehow, in a way that we can sort of explain, we can say that the highest probability is going to be around the correct phase. But it's not going to be 100% concentrated on the correct phase factor. Instead, when you apply the Fourier inverse, the probability is going to spread out along all the numbers 0 to 2t minus 1, but the probability is going to concentrate around the correct phase factor. And we need to quantify that, because there's going to be many cases where things don't terminate. Questions? Right. Benjamin?
So it's u to the 2, is it u to the 2j minus 1 or u to the 2j minus 1?
The exponent is j minus 1.
Oh. Is it j there, or is that a t?
That's the last one. That's a t. Because that's the last one. And it's increasing by powers of 2. So it starts at u to a 2 to a 0, u to a 2, u to the 4, u to the 8, and so on, up to u2 to the t minus 1. Another question up here?
It's just, so you're basically, you're sort of limited in your resolution by the number of qubits you have.
Yeah. And so, yeah, so next what we want to do is quantify how accurate our measurements are. So this is the claim for the accuracy. So we're going to start again with a unitary operator u that has an eigenvector u and it has a phase phi. Then we're defining phi tilde to be the result of this the same quantum circuit. So we're going to apply the same quantum circuit, but now we don't know that phi has a terminating expansion. So the result is actually going to be a superposition of different states of different numbers. Whereas if it had terminating, if phi terminates, so these are t qubits, and let's say 2 to the t phi was an integer, then this would mean that phi tilde in here is equal to just one number, phi bar. So the whole probability is concentrated on phi bar. But if it's not, in general, it's not going to be terminating. So the probability or the states, it's going to be a linear superposition of different numbers. And it's going to be concentrated around the closest approximation of the phase. So again, if it terminates, meaning that 2 to the t times phi is an integer, then p bar is just going to be a single number. If not, then it's going to be a linear superposition of different numbers. And the probability is going to be concentrated around an approximation for phi. And this is what we want to quantify. So in here, moreover, we're going to introduce this phi sub b, which is the closest. Phi sub b is going to be at essentially the closest terminating expansion of phi that approximates the phase. Essentially, what you're doing is you take phi, you take the expansion, and then you cut it off at the teeth unit, or the teeth number. So you make the expansion length t. So it's going to be you're going to truncate the phi to be phi of b over 2t. So this is going to be the closest you can actually get measuring only t qubits of phi. So we're going to call that phi of b. And then the claim is that the probability that we measure a number, so m is going to be the measurement we get from one of these guys. So the probability that if we measure something and we look at the distance from phi of b, phi sub b, the best approximation, and we say that the distance between these two is greater than 2 to the t minus n, or if we put it into the decimal, into numbers between 0 and 1, the probability that the measurement is further than 2 minus n minus 2 to minus t is going to be bounded above by this quantity, which we'll just call epsilon. So this is saying that the probability that we measure something far away from phi of b is bounded by this quantity. And in here, I haven't really told you what t and n are, but in here, t, n is you want to measure phi accurate to n bits, and we're going to have n is less than t. And t is the number of qubits, or the number of qubits that you need to measure within n bits, to accurate to n bits. So in here, that means that using this bound, that means that you need t qubits, which is roughly n plus log base 2 of 2 plus 1 over 2 epsilon, to measure phi accurate to n bits and with the probability bounded by epsilon. So for instance, if you want the probability to be equal to 0, so if you fix n, the accuracy that you want of the number of bits, and you want it to be 100% accurate, then you need to send epsilon to 0. And that means that this, the number of bits that you need, t, is going to go to infinity. So you need an infinite number of qubits to actually measure the phase accurate to n bits. Or if you want to measure it, or if you fix the probability epsilon and you want to measure it accurate to like a large number of bits, then you're going to need a lot of qubits to measure it accurately. So there's two things that affect your measuring, your approximation. It's how many bits you want it accurate to, and with what probability, epsilon. And epsilon here is measuring the probability of how far your measurement is going to be from the true best approximate using t qubits. So in here, what this is saying is that if we use the same quantum circuit as we did for the terminating case, then it's not going to give us a perfect answer, 100% accurate, but it's going to give us an answer that's close enough that we can control. We can control how close it is. And for this claim, I've decided to skip the proof. I think the result is intuitive. If you want it more accurate with high probability, the number of qubits that you need needs to go higher. And it's basically a computation and just trying to bound certain terms. So essentially, what you want to do is that you want to compute these amplitudes given the circuit here. And then you want to compute the probability of the amplitudes that are far away from phi of b, phi sub b. And you can actually control that, and then you just use some geometric series, and then you can bound the probability by knowing what these coefficients are going to be. Questions? All right, so now I want to start making way towards the factoring strategy. So in here, the idea was that we were going to take an x. So in here we take x whose GCD, x and n is equal to 1. And R is the order modulo n. So we have this set up, and also we assume that R is even. Then the punchline is that one of these two numbers is going to be a non-trivial factor of n. So this is going to be our factoring strategy. And to implement this, in a quantum circuit, we need a unitary operator to actually figure out what, we need a quantum circuit to figure out what R is. What the order of x modulo n is. So somehow that's information that we really need to factor n, R, figuring R. And the way that it's going to work out is that R is going to pop out of a unitary operator as a face of the unitary operator. And we're going to use the face estimation to approximate it. And then we're not going to measure it 100% accurately. So we're going to need to figure out another way to, given an approximate value of R, how to actually find what R is. So that's going to get a little bit tricky, but first we need the operator that's going to give us the R. And here we're going to introduce this following operator. So this is going to be for vector space of dimension 2 to the L. So where the basis is just 0 to 2 to the L minus 1. And this is just going to be a multiplication operator. So it's going to take y, and it's going to multiply y times x modulo n. So this is going to be our unitary operator. And in here, I took a moment to actually prove that ux is unitary. And in here, here's the proof. And the question is, so in here to show that u is unitary, it's equivalent to showing that u dagger is equal to ID. And in here, I'm essentially computing this is the ij entry of the unitary operator as a matrix. So I'm computing this ij entry to compute the ij entry of the dagger version, which is just going to be uji complex conjugate. So I just compute uij so I can figure out what uji is, or what the ij coordinate of the complex transpose is, and then I check the identity that u dagger u is equal to ID. So in here, I start by computing the uij entry, and in here, it's just multiplication by x. And in here, these are going to be basis elements, which are orthonormal, and which means that this is going to be either 1 or 0, and it's going to be 1 if I is equal to xj. And this equation is equivalent to this equation, x inverse I equals j. So that means that I can write this as this equivalently, which means that u dagger acting on I is equal to x inverse I mod n. And that means that u dagger u is equal to u is first acting as x, and u dagger is then acting as x inverse, so it's just going to be I. So u dagger u is just going to be the identity. Here's the question for everyone. Where did I use the condition that the GCD is equal to 1? Or did I use it? Bum, bum, bum. Because for instance, let's say if x is equal to n, would this work? So clearly, if x is equal to n, the GCD of n and n is not equal to 1. It's going to be n. So would that work? I claim that it doesn't. So I must use the condition that the GCD is equal to 1. But where?
Isn't that the requirement to say that x has inverse?
That's it. So because the GCD is equal to 1, we can actually go from here to here. And so to actually make sure that u of x is unitary, we actually need that the GCD is equal to 1. But this is something that we want in our factoring strategy. Now, this is an exercise for you all. So we're going to take the vector u sub s, defined in here. And you're going to assume that the order of x modulo n is equal to r. And now the question is show that u sub s is an eigenvector of ux and find the corresponding eigenvalue. So I'll give you a moment to figure that out. All right, take a moment to check with your neighbor.
Start by multiplying by us on the right. Then use linearity. So ux times us. And then you make the ux by linearity to right here. And how does ux act on this? Multiplies by x. So this is going to be x equals 1 y.
So yeah, I'm running on low sleep, so I just kept making mistakes writing it down, so I forgot to write it down.
It's supposed to be ux.
Oh.
So it's going to be, we have it, it's
It's
x.
So is that the x up there too?
No, it's the vector is u sub s,
Oh,
and the operator is u sub x. So that will change.
so it's f k plus
Yeah.
okay.
And yeah, the idea is then to match the case together, so plus or minus 1 equals 2. Plus or minus 1.
Alright, dude. Well, we got it to there.
Where's this mark? No. Well, ux is the price of x by taking the product. So it's going to be what? Yeah. So I'm going to try to simplify it and then after that. No.
Yeah, I got to this point, and I thought that, because he wants to make this exactly
Yeah,
this,
I
we just
there.
take, input
Yeah.
0.
And if there was a k,
Well, basically,
like just keep the k
function is now where we
just keep the k inside. Just keep the k inside.
Yeah, this is not what I read this. No, I realized that I summation.
Yeah. So here,
turn it
do
through.
This.
plus or minus 1.
So this will turn
Yeah.
into x to the r,
K.
but
So in the
x to the
exponent?
r is the
So
Oh, what if I,
Yeah. So I do
Oh, so the UX shifts
S
into
and
to
K
add
Yeah,
plus 1
yeah,
minus
the UX,
K
because
plus
the
1 minus
the
1.
action of UX is
So what I want
this,
is I want to have
is this
say
times
K plus 1 over
x
K plus 1
mod
here.
Yeah.
but that's just,
Sure.
And then then I'm going to factor an E
you get all the way up to x to the r now.
and E to the
That's the same thing as 1.
KS R. Yeah, plus or minus 1 here. Because you want to match this K plus 1 with this K. So you want plus or minus 1.
Oh,
Ooh, look at that.
is that the same, that's the
This is
same one?
it goes
Yeah,
up
same
to
here.
K minus
That's the first one.
Now in here, in this, you want to match this K plus 1 with this exponent here, so you do plus or minus 1. And then you factor out the 1.
Nice.
Did you guys get anywhere?
Yes. I mean, we were talking about this and then they can match up the terms, and now it's just factors.
Okay. Same place?
Yeah, so it's like, yeah, minus.
Alright, seems like everyone's getting to roughly the same place. So here's the details. So I just applied UX. And in here, by linearity, I can bring the UX inside. And applying UX is just multiplication by X. So this is xk plus 1. And what I'm doing here is that I really want to match this exponent with this. So I add 1 and subtract 1 to my k. And then I keep the plus 1, and then I factor out the minus 1. So I factor out this term. And now this case match, and we're going from 0 to r minus 1, and since it's modular, it doesn't really matter. So this term, it's going to be the same as US. Bless you. Bless you. And so the eigenvalue is going to be this.
Can you explain that last step where we can write that as just US?
Yeah, so in here, this is going to be, so if we look at this, just looking at the xk plus 1, so this is going to be, if we start at 0, we're going to have x1, and then the next one is going to be x2, and then it's going to go up to xr minus 1, and then x to the r. Whereas before it was, if we're like right here, it was going to be x to a 0, x to a 1, up to x r minus 1. But the trick here is that the order of x is r. So this x to the r is equal to 1, and this x to a 0 is equal to 1.
In the exponent, they will still have different phases.
No, because they match, and it's going to cycle through it. So if you look at the r minus 1, 1, so the last phase, it's going to be e to the minus 2 pi I r s. If you look at the last one, it's going to be e minus 2 pi I s r over r. So it's going to be e to the 2 pi I s. This is going to be equal to 1 because s is an integer. And in the first one here, it's going to be e to the minus 2 pi I s times 0, which is also equal to 1. So because it comes back, it does a full, it cycles through the roots of unity in the circle. And the x to the r's are also cycling. So it's just gonna be shifting.
So what is S?
S is a number between 0 and r minus 1. So maybe I didn't say that explicitly. So it's going to be a number between 0 and r minus 1. An integer. And so it's going to cycle through them. And instead of starting from the first one, you start from the second one. But it's going to be cycling through them. So the summation is going to stay the same. Does that make sense?
I think so.
So yeah, try to look at it. You can write it explicitly. You go write the face and write the x's and see that they match. And the punchline here is that in the face, in the face of US, you have the r that you want. And that's what we want to extract. But the tricky thing is that we can only measure it up to certain accuracy. So we're going to have to do more work to actually extract r. All right, that's it.